All right, how's it going, everybody? We are here on Friday, March 5th. Today we're going to be talking about section 7.7. We're going to be solving some trig equations today. Before we get started, I want to talk about the events above my head right here. What's going on for our next 3 weeks? So right now we're in week 8. Week 8 is our week immediately before spring break. So spring break is next week right here, woohoo. So officially, week 8 is like starting on Monday, March 8th, right? It's March 5th right now. I'm making my video for the next week. So March 8th through 12th is a Monday through Friday. That's week 8. Spring break week is the week that follows that. That's March 15th through March 19th. That's our spring break. Uh, Apparently, much to my wife's dismay and discomfort, my daughter is choosing to hang out inside of her for a little bit longer here. I was heavily anticipating either last week or this week being baby arrival week, and that does not seem to be cropping up right now. So it appears like we'll be doing a regular week 8 and going on into spring break. What that means is that it is for sure that our baby week, our canceled week, and it's not canceled. It's not canceled. We're just not covering any new content that week, right? So we're going to have spring break week is the week after week 8. The week after spring break, we're going to have baby week, which really just means no new content, no regular homework, just a midterm, right? So what's going to happen here is sometime towards the end of spring break, I'm going to send out a Canvas announcement, and in that announcement, it's going to say something like, these aren't the exact figures here, but it's going to say something like, I'll be posting your midterm on Tuesday at noon, and it is due in Canvas by Thursday at 5, or something like that. Those aren't necessarily the dates or times right there, but the point is, at the end of spring break, I'll send out an announcement so that you know what like 2 or 3 day chunk of time you're going to be expected to take your midterm. And then it'll end up getting posted in Canvas. So in the week 9 module in Canvas, week 9 being the week after spring break, the only thing that'll be in that module is just the midterm, and that's all you're responsible for in that week. Week 10 will be the 2 weeks after spring break. That is starting on March 29th. March 29th then is our like return to regular content, because we're going to have, week 8, week before spring break week, no content, midterm, baby week, no content. So there's really 2 weeks where we're not covering new content and then getting back into this. So essentially, like 3 weeks from now is basically where we're going to pick back up with our content again. I am kind of unhappy and also kind of very happy about the way that this is kind of getting split, just the way that things worked out here, that we're covering part 1 of trig equations in this video, and that we're not doing part 2 of trig equations until 3 weeks from now. I think that this is one of those things that's great for us, because these are hard and these are something that we absolutely need to sort of look at twice. And I have the fact that they're really spread out means that you guys are gonna forget some stuff, and then you're gonna be reminded of that stuff again. I think that this is one of the most important things that happens in this entire class is solving trig equations. And so I'm happy that it is over 2 sections, and I'm happy that it is naturally occurring that these will be as separated as possible for 2 adjacent sections in this class, meaning that you get like sort of to see the whole thing a second time, basically. But 7-8 is certainly the hard one. This is 7-8 is like advanced trig equations, whereas today we're going to get kind of our basics down. All right, so those are our next 3 weeks coming up right here. So just kind of remember, next week spring break, week after that, you're just going to take a midterm. And I will also say, this semester I'm in general I've become a softie about deadlines, which didn't used to be who I was, but online I feel like that's a more responsible thing for me to do. The midterm is not one of those soft deadline things right there. The midterm is like the one thing all semester aside from the final exam where it's like, this is the time that it's due, and if it's not submitted by then that's going to cost you a good chunk. So don't screw that up. It's your own thing to do the week after spring break. Make sure you check at the end of spring break. Just check on Monday when we come back. Look in Canvas, and you should see an announcement from me the Monday after spring break. And at the very, very, very latest, it'll be on that Monday after spring break, where I will have sent you a message that will tell you exactly when to expect me to post the midterm and when I expect you to submit your completed midterm. Don't miss it. It's going to be happening the week after spring break. Be ready for that. So let's talk 7-7 today. Let's solve some equations today. So we've spent all of chapter 7 learning how trig equations can be rephrased into other more simple trig expressions. I put rephrased in quotes right there just because that's a weird math word to use, a rephrasing. That's like an English word right there. But all we've really been doing is just converting quantities into other equal quantities that just look different. So it's sort of just like phrasing something different. This is exactly our 6 of one, half dozen of another. That's a rephrasing of two identical expressions right there. Right? The other words I put in quotes there are more simple trig expressions right there. I don't really like the concept of when math textbooks just say simplify, because in my mind I say, well, simplify for what purpose? We have a purpose now. We are simplifying for the purpose of solving an equation using the expressions that we have. So what we're going to see, and then we'll see a little bit more of this in 7.8 than in 7.7, but we're going to see situations where certain expressions don't look too crazy, but they're going to be difficult to manage when we want to solve an equation. And by converting them into other expressions that might not look any nicer, it's actually going to make things much, much easier for our equation solving. So these rephrasings into trig expressions that are more useful, maybe that's what I would say, rather than more simple, is going to be an important part of this right here. So today we'll look at our simple solving scenarios. And even this stuff isn't, it's not like it's just straight up easy. There's still some components of this that are a little bit tough right here, but it's certainly more simple than the stuff that we're going to see in 7.8. So it really matters that we sort of master the easy ones here today so that we can handle the more difficult algebra associated with one that we're going to see in 7.8. Our big concept for today is to understand how many solutions trig equations can have and how we should express these. One of the things that we're going to find is that if you're used to solving algebra equations saying solve for x, it's incredibly typical for you to find a single one solution, right? Or maybe if you're solving a quadratic equation, two solutions, stuff like that. What we're going to end up finding is that a vast majority of all of our trig equations have way more solutions than that. And so managing the large number of solutions that we're going to end up seeing is going to be one of the challenges that's associated with this section, certainly. I'll also say that today is kind of one of those days that I really like. That today isn't really based on definitions or formulas or anything like that. Today is just like we're solving some stuff. We just want to make sure we got it all. We want to be able to like check some answers, stuff like that. So this is very much a learn by doing day rather than oh, let's define these 6 quantities. So I'm going to say to you, there's not really any formulas or theorems or definitions we need to discuss. Mostly just strategy. So it's going to be done by doing. And that's a tiny lie right there. There is sort of one definition that we need to discuss, but we're just going to discuss it once we get into our first example here. And that's this distinction that I lightly talked about at the end of the last video of distinguishing between general solutions and particular solutions right here. So we'll see this in our first example right here. So let's just get into this guy. Our first example, I would like us to solve the equation sine of theta equals 1/2. This is a pretty dang simple trig equation right here. And I am saying to you, and I know that we haven't quite described this yet, to find the general solution and then list all the solutions that are in the interval from 0 to 2 pi. This is our particular solution, our solution associated with one particular interval of theta. Right? So what we need to recognize right here is a really important thing. So when we're going about solving this equation, what it means to solve an equation is to find all of the values of the variable that make the equation true, right? What are all of the values of theta that results in sine of theta being equal to 1/2? Well, one thing I think that would be smart for me to do with this guy is to sort of start by drawing a little bit of a unit circle right here, right? And I'm thinking to myself, I know that sine's job is to measure height on the unit circle. And I always draw this so that my chunky part of the circle is right where I'm interested in it. I'm picturing to myself, there's a height of 1/2, so I'm interested in this location on the unit circle, or perhaps this location on the unit circle right here. So I'm thinking to myself, this to me looks like our 30 degrees or our pi sixths. So just by doing a little simple starting with sine of theta equals 1/2, if I were to take the inverse sine on both sides, then I would be getting theta equals sine inverse of 1/2, which you guys have learned to tell me is going to be theta equals pi sixths. This is one solution. Right? Now, the reason that we're getting pi sixths here is because we're remembering that sine inverse, sine is measuring heights, So remember that sine inverse is this function that we have defined to only ever give outputs over here, right? This is where sine inverse lives. This is sine inverse's home right here. But that doesn't mean that there's not other angles that could also result in us getting a sine of 1/2. This is just what sine inverse is going to tell us about. We also know by symmetry that, and here's my other one over here. I'm going to rewrite that since that didn't work out. I'll write this one in blue. We could also go in this angle over here, right? This guy is also going to be giving us another angle at which sine of theta is equal to 1/2. I can tell that's true because the height of this point is 1/2. It's the exact same height as this point over here. The sine of that theta is 1/2. Sine is measuring height on the unit circle. You should notice that we're never going to get out results like this angle right here from using just inverse sine, because inverse sine is always only going to give us this stuff on the right-hand side over here. So notice that we do know that we have this other solution. This looks like 1 pi sixth, 2 pi sixths, 3 pi sixths, 4 pi sixths, 5 pi sixths right there. Now, so this is good. So notice that one thing that I did here is I directly solved the equation using an inverse sine, and that did get me one solution. Right? Now, my question to you is, do you see any other places on the unit circle where we get to a height of 1/2? And I would say, well, no. It seems like those are the only two places on the unit circle we hit that height of 1/2, right? So it seems like these should be our two solutions in the interval from 0 to 2 pi. It seems like these are the only ones. But then I would say to you, are there any other solutions outside of 0 to 2 pi that should also make this true? Well, you know about coterminal angles. What you know is that there are actually an infinite number of angles that all land on pi sixth, coterminal with pi sixth, but include additional bonus revolutions around it, right? So what I'm thinking here is our general solution for this guy right here, for this theta equals pi sixth, is we should be getting theta equals pi sixths plus, how do I get to my next version of this? Well, I do another lap and I land there again, and I do another lap and I land there again, and I do another lap and I land there again. There's an infinite number of solutions to this equation right here, but we want to state this simply. It's not like I'm going to make a list that's infinitely long. So what I'm thinking to myself is, how do you proceed from pi sixths to get to the next version of it? Well, you'd go ahead and add 2 pi. And then I'd say to you, how many different times should I add 2 pi? And you should say to yourself, well, 1 or 2 or 3 or 4 or -6 or 47 or -1000. All of those would be an acceptable number of additional rotations to do, forwards or backwards, positive or negative, from pi sixths to land at pi sixth again. So what I'm going to say here is 2 pi k, where k has to be an integer, right? It can't be like you're going to do 2 pi times the square root of 3, then you'd be landing at some other place on the unit circle where we wouldn't have that sine of theta is going to be 1/2 right here. So this is my particular solution inside of 0 to 2 pi. This is another particular solution inside of 0 to 2 pi. This is my general solution associated with the pi 6 solution. It seems like it should be the case also that we could do additional rotations to get to this guy over and over and over again as well. So it does seem like we're going to get a general solution associated with this guy as well of theta equals 5 pi sixths plus 2 pi k. I know that the sine function repeats every 2 pi, and that's part of the big reason why I'm using 2 pi right there. That's how many more radians of revolution I need to do to get back to that same location once again. So again, there are an infinite number of different angles that we could throw into this function that would all produce 1/2. Pi sixths, 13 pi sixths, I got to add 12 sixths again, 25 pi sixths, 37 pi sixths, 49 pi sixths. All of these will work, and you could go on forever. We're trying to come up with a generic way to phrase these guys, and this k is this genericness. This says do k number of extra revolutions from pi sixths. So let me kind of write out some of this stuff right here. So our overall general solution to sine of theta equals 1/2 is theta equals pi 6 plus 2 pi k, and theta equals 5 pi sixths plus 2 pi k. And I want to break this down in words real quick to make sure that we can read this here. And when I say a revolution, I really mean 2 pi radians. Right? So that's what we mean when we're writing that expression there. Saying starting from pi sixth, you can do any number of 2 pi additional amounts of rotation, and that will just keep on landing you back at that location that is equivalent to pi sixth in terms of the sine function right there. So that's what we mean. So this is our general solution right here. And then I want to say also the particular solution. Particular solutions So in this case, I specified the interval 0 to 2 pi. So my question to you would be, which of the solutions fall in that interval? Well, it looks like here, if I were to even do k being one additional revolution, then we'd be getting something that's more than 2 pi. It'd be 2 pi plus pi 6. That's bigger than our upper bound. Same is true right there. So in this case, we found the two particular solutions as the kind of first things. Pi 6, 5 pi 6. Those are the only two solutions within one revolution. But there are technically an infinite number of solutions based on the infinite number of bonus revolutions you could have done before landing at something that lands at the same place as pi 6 or 5 pi 6 that's out there, right? So it's very often the case that you'll be asked for one or the other or both of these. So you need to distinguish between these. Anytime a question asks you for a general solution to a trigonometry equation, that's because we need to make that distinction because trig equations in almost all cases have an infinite number of solutions. And so we need a way to concisely represent all of those infinite solutions in one simple statement. And the k is what's really handling that. There are an infinite number of values that k can take on, and those are going to help us get to the infinite number of solutions that are available. The reason why we're multiplying by 2 pi in this case is because sine has a period of 2 pi. It repeats its behavior every 2 pi. So it says go 2 pi further out in the future and you will get the same behavior as we had at pi 6. And our little kind of our bonus statement here that I said but I didn't write is that k must be an integer. Positive or negative. That just means a whole number, positive or negative. This just means don't try and stick in 1/2 for k. That's not going to get you there because going only 1/2 of an extra revolution doesn't get you to something that's coterminal with the original solution, right? So our general solutions always will have a k in them. Our particular solutions are always tied to some specified interval that's been provided for us. Often it's 0 to 2 pi or 0 to pi or 0 to pi halves, but I'll probably do something weird to you like say from negative 4 pi to negative 2 pi. And you'll have to play around with plugging in some numbers for k that are associated with that. And I should make one more comment just to be very, very clear on all this. Here, both of these are tied to k equals 0 above. But that won't always be the case. That just happened to work out here, that k equals 0 was the only k that we considered to get the ones that fell in here. But if in general there was going to be more, then I would say, well, let's try k equals 0. Now let's try k equals 1. Now let's try k equals 2, and just keep on going until we fall off the end of our desired interval. I could just tell right away that if k was even 1, then both these numbers would be too big to fall in our interval, so I didn't even go out there. I just used k equals 0. Just keep pi 6 and 5 pi 6. Seems to be the only two that are within one revolution right there. All right, cool. So there's our first one. And again, our keywords here are general versus particular solutions. All of your general solutions will have k in them to indicate the infinite number of options that are out there in a tight little multiplication. 2 pi k, we'll see some like pi fourths k's. That number will change. It's not always a 2 pi k, but that k is kind of indicating there's an infinite number of choices of k directly tied to our infinite number of solutions associated with this equation right here. I think a good thing to do is very briefly, let's go poke on over to Desmos and confirm that this is in fact going to be the case. So here we are in Desmos, and we can do this. We can just ask Desmos, what's up with sine of x? And what I want to do is not do equals 1/2 right there. Watch what happens if we do. It gives us a bunch of vertical lines. Those vertical lines are our solution locations, but that's not a helpful graph for me. I want to also graph y equals 1/2. This is like graphing y equals sine of x, y equals 1/2, and finding where are they the same as each other, where do they intersect. And what you can see is, yeah, the green line and the red line, or the straight line and the curvy line, are going to hit each other an infinite number of times, right? This graph just goes on forever. We can see there's an infinite number of intersections. What I can see is where they hit each other. Oh, look, pi 6 and 5 pi 6. And our next one, 13 pi 6. That's more than 2 pi. So that's not what I was interested in there, right? Maybe I could even go so far as to say 0 less than x less than 2 pi. And now I can see there's my domain I've added in there. And it looks like we only hit it twice. We would have to go beyond 2 pi to hit it a third time out there. So good graphical justification of our answer here in Desmos, right? Let's go ahead and take a look at our next example here. Find the general solution to the equation 2 cosine theta plus root 3 equals 0. The thing that you should notice about this one right away is that it's not quite like just solved for a trig function like we want it to be. So one of the things that you need to start getting comfortable with is the fact that we're going to have to use all of our algebra skills in solving these trig equations here. We need to do some algebraic steps associated with this as well. So it looks like starting from 2 cosine theta plus root 3 equals 0. My goal is to solve for theta, so I'm trying to like remove all of the other parts that are associated with this, right? So my first algebra step here should be to subtract root 3. Now I can go ahead and divide by 2 on both sides. And now I think this is a good place for me to use a cosine inverse to solve this, but I know that I had a lesson to learn in the last one, which is that when I did the inverse sine of 1/2, it only gave me one of the infinite number of solutions I needed to find. Now, it was a really helpful one, and I could draw a picture to help me realize what the other was going to be, and then use those to form my generals. But like, this isn't just apply an inverse sine once and call it good, right? That's not really what's happening right here. So I am thinking to myself, based on my unit circle right here, I am expecting to get out from the cosine function negative root 3 over 2. Obviously, this problem was set up very specifically to give us a value that we recognize right here, right? So this is saying to me, cosine is measuring how far left-right we are on the unit circle. I can see that because it's negative, we're going to be on the left of the unit circle. And I can see that we're going to be pretty far to the left on the unit circle here, right? That means that it looks like we're going to be going, root 3 over 2, not just 1/2 to get to that point. So here is my x value being, negative root 3 over 2 right there. And it seems to me like these are the two locations that we should be arriving at right there, right? Now, I know that my root 3 over 2's, those are associated with my 30 degrees and my 60 degrees, or my pi thirds, my pi 6. I'm saying that because it looks like I drew this one as like a 45-degree angle, but I know that's my root 2 over 2 type of angles right there. So I'm thinking to myself, this should be where we've gone this should actually be very, very similar to our previous answer, actually. It looks like this is going to be 1 pi 6, 2 pi 6, 3 pi 6, 4 pi 6, 5 pi sixths, 6 pi sixths, 7 pi 6. So using my unit circle or my ideas of symmetry, I can see that this is associated with, so I'm going to say here, cosine inverse of negative root 3 over 2 should be equal to 5 pi sixths. And again, remember that our cosine inverse function is always only ever going to give us the top half of the unit circle. So if you're interested in all the possible things that could have gone in there, then you need to be able to consider not just half of one circle, but all of any number of revolutions, right? So by extending this to the full circle, that's where we get our other solution of 7 pi sixths. Then by considering additional revolutions, that's where we get to our plus 2 pi k term that we're going to stick onto this thing, right? So this is our cosine inverse of x right there. Remember, it always lives up there. By symmetry, unit circle, we also get theta equals 7 pi sixths. Seems like it should also work out right there. Now, notice in this case, I was asking you specifically for the general solutions, and I didn't even care about particular solutions. So it's true that these are two of the solutions that are associated with this guy right here. I know that I could also just do additional laps, right? I'm thinking to myself, all right, from 5 pi 6, you could just go 2 pi further, and then 2 pi further. Or we could have, starting from 5 pi 6, undone one whole revolution, minus 2 pi, minus another 2 pi for minus 4 pi, minus another 2 pi for minus 6 pi. All those ones out there would land us at the same location. All of those values would have a cosine of negative root 3 over 2. So it looks like my general solution for this guy is going to be theta equals 5 pi sixths plus 2 pi k, and theta equals 7 pi sixths plus 2 pi k. Those are my two sort of infinite families of solutions that are associated with this guy right here. So notice this is really, really hard for me to do if I can't draw a unit circle and recognize some values on it. The unit circle, this picture, every single time I solve a trig equation, I'm drawing a unit circle. And I'm still doing that, and I've done this a billion times in my life. Draw yourself a sketch. Do yourself a favor. Mark off pi sixths and pi thirdses and draw a little line. You know, you're looking for an x value of negative root 3 over 2 because that's your cosine value. Draw the line x equals negative root 3 over 2 on there. Intersect your unit circle with it, right? Do that kind of stuff for yourself. Let's go verify this guy in Desmos here and feel good about our answer. So notice here for this guy, I'm going to be throwing into Desmos this whole equation here on the left as 1y equals. I'm going to throw in y equals 0 as the other one, and we're again going to look for their intersections. So we're looking at, and I'm going to leave that domain on there, by the way, y equals 2 cosine x plus square root of 3. And down here, I really wanted that to be the same thing as 0. So you should notice that there are only two solutions in 0 to 2 pi, just like we found. They are located at 5 pi 6 and at 7 pi 6, just like we found. But in this problem, we weren't interested in the particular solution with that restricted domain. We were interested in all of them. And so you should notice that we could add 2 pi to 5 pi 6, and that will get us to 17 pi 6. That's 12 pi 6 has been added to get us there. We could add 12 pi 6 or 2 pi to 7 pi 6 to get to 19 pi 6, and we just keep on doing that. There's another revolution to get around, right? All of these are solutions. So rather than writing an infinite list of numbers, we come up with a more concise way to do that. The k is handling the infiniteness here for you, the repetitions that are out there. Right? So this example is very similar to the previous example. The only real difference is we actually had to do a little bit of algebra first to isolate the trigonometry expression. Then we had to interpret using the unit circle where all of our solutions might end up living right here. Right? So let's look at this guy right here and see that we're going to end up this one, hopefully, I mean, look at this one and recognize that this should look to you almost exactly the same as the one that we just did. There's just going to be one extra little inconvenience associated with this one that's going to make us have to be a little bit more careful with the math that we're doing right here, right? So again, this looks very similar to what I was just thinking a second ago, so I'm not going to do much different here. Again, always undo your addition and subtraction first. Always undo your multiplication and division second. Now, my question to you is this. Do you know any angles that result in an output from the sine function of root 3 over 4? And the answer to that is no, you do not. I am confident that you do not. This is not anywhere remotely close to one of our clean trig outputs right here. This just is not something that cleanly comes out from any reasonable angle on a unit circle out there, right? This isn't one of our known outputs from a known angle right here. So my bit of inconvenience here is this. In our previous examples, I was able to like literally mark off pi 6s on the unit circle and be like, oh, I know that I'm at this one. I know that I'm at that one. I'm able to give these as exact numbers right here. 5 pi 6, 7 pi 6. There's no estimation going on right here. This is just going to be some crappy angle out there that's not some nice number like pi 6, right? It's just not going to be one of those nice easy ones. So we're here going to have to rely on our inverse trig function and our unit circle to get us the values that we're interested in. So here's the thing that I know. I know that on my unit circle right here, I am interested in seeing all of the angles that will give me whatever this height is of negative root 3 over 4. So height on the unit circle, that's my y measurement, right? So it should be that there's some y equals, negative root 3 over 4. I don't even know what that decimal is yet. I'm not that worried about it. There should be some height though, and I know that whatever I'm going to get out from my inverse trig function, I know it's going to give me one of these two values, and I know that I am responsible for coming up with the other one. So I know that my inverse trig function is going to give me this one that's on the right around my green parts right here. And what I know is that my inverse sine function is never going to tell me that one, but I need that one. So I need to be able to interpret the symmetry that's associated with that result right there. Right? So it looks like this is what we're going to get from inverse sine. This is what we need to interpret for ourselves right here. We're going to have to figure out how to do that. So it seems like I'm going to get theta equals sine inverse of negative root 3 over 4. Well, I don't have a nice value for that. The best thing I can do, oh no, so I've discovered that oh, there it is. My child has discovered that this is the best play toy over at my desk. Thank goodness, because everything else is actually expensive and breakable, and this is not really expensive or breakable, but it disappears often now. So I'm going to go to my calculator, and I'm going to hit it up for sine inverse of root 3 over 4. I'm going to make sure that I'm in radian mode first, since I'm going to talk about all these things in radians here today, and I'm going to do my inverse sine of negative square root of 3 divided by 4. Don't forget that negative in there. And my calculator is telling me, let's see, my calculator is telling me negative 0.4478. That's what I'm getting out from my calculator. I believe that right there. I mean, it seems like a moderate. It's not like we're getting like 1, and it's not like we're getting 0 out from this right here. So something in between there, about halfway in between. It's good with me. So this says to me that this guy right here must be our negative 0.4478. So the question for you is then, where is this going to be? Well, the reason I keep on using this phrase by symmetry instead of by the unit circle is because we need to be able to handle these symmetries now. So here's what I'm thinking. If this angle right here is what we're calling theta, then how are you going to tell me what angle we get to over here, right? And here's the way that I think about this. Sine and cosine are not generally always, so the question is being asked here is, are sine and cosine always used with radians? No. If you did this guy in degrees right here, you would get just an equivalent answer in terms of degrees. The reason why radians work out nicer is because once you get to calculus, what you'll find is that if you do all of your trig math in calculus in degrees, it will introduce an extra term that you need to multiply by every single time you apply a calculus operation if it's in terms of degrees. And with radians, you will not. And so it is very typical for Calc 1 and above forever to pretty much exclusively use radians because it results in there not being an extra multiplier popping out of all of your expressions every time you apply a calculus operation. So all this stuff could be done in degrees for right now. I'm just going to use radians for all this because for all of us that are going to go take calculus, calculus will always be done in radians because that is like I keep on saying, otherwise when you do your derivatives and integrals in calculus, they will be popping out extra constant multiples you'll have to deal with if it's in degrees, and that doesn't end up happening if you're in radians. So that's the only reason I'm doing all this in radians here. So what I want is I want to know what this angle is over here, and here's the math there, the visualization I'm going to do to get to it. Rather than starting at 0 and going in the negative direction by 0.4478 radians, I'm instead going to maybe think to myself, I can go ahead and go negative pi as my starting amount, and then doing a positive amount of rotation by 0.447. So my two-step process here is do negative pi and then go back by 0.4478. And that will land us at exactly this place that we want it to be at. Right? I wrote that too small right there. So that's my sort of like mental process to get us here right there. That guy right there, that's our negative 0.4, or excuse me, that's our positive 0.4478 because I did it in the appropriate counterclockwise direction. That is our positive direction of rotation. So I can see here that by symmetry, theta equals negative pi plus 0.4478 is also a solution. And I'm going to talk through this one again because I am positive that most of you didn't follow along my motions here, right? When I say a negative amount of radians, that means I'm going in the negative rotation direction. So we went negative 0.4478 to get to that one that I labeled in green right here. But to get to this one over here, there's several different ways that we could have done this, right? One of the ways that I could think to do this is we always are starting at 0 right here, right? From 0, I could think to myself, let's start by doing a negative pi rotation to get all the way over to here. So I've done negative pi. There's my negative pi. From here, it looks like I can do the positive amount of rotation of exactly this number. And that will land me at this point right here. So that's why I did a positive version of 0.4478 right there. And I diagrammed it not well over here, right? Starting here, I first did negative pi rotations, then I did a positive 0.4478 rotation, and it landed me at this point that's going to be perfectly symmetric with the one that's the first one that we found over here. And notice you could have phrased this many other ways. Notice another way to have done this would have been starting at 0, first do pi rotations, then do the positive 0.447 to get the rest of the way there. And notice that positive pi plus 0.447 versus negative pi plus 447, those differ by 2 pi. And that's exactly what the 2 pi is going to be handling, the 2 pi k in our general solution. So it doesn't even matter which ones of those you were to do right there. So I'm even going to write that here. I'm going to say, notice could have also been theta equals positive pi plus 0.4478. Pi. And the fact that they differ by 2 pi means that's exactly what's going to get handled in our general solution statement right here. Okay? So what I'm going to say now for my general solution for this guy now is going to be, it looks like my general solution is theta equals, and my first solution was this guy, so the negative 0.4478 plus 2 pi k, because I know I could just do additional revolutions and land there again, and theta equals, and I could state either one of these. Either one of these would be correct right here. It doesn't really matter. I guess the thing that I'm thinking is it's pretty typical to always list, well, I even broke the rule right there. This is really saying that we're specifying a bunch of evenly spaced points on a line, and I know that the spacing between them is 2 pi. You just need to pick literally any one of the points to define all the rest of them because I know what the spacing is going to be. So either of these would be acceptable right here. So I might say something like pi plus 0.4478 as sort of like my angle right there, plus 2 pi k. Um, Technically, there's some light algebra you could do to combine this pi and this 2 pi k. I don't think that's a good idea, even though it could be done. I want to see that the 2 pi k involves my repetitions, and I want to see that the term inside that's leading out in front of it represents sort of like my particular solution in 0 to 2 pi out there, right? So the whole point of the annoyance with this one is you don't get your nice angles to deal with all the time. So if you come up on a value that's one that you don't recognize, like root 3 over 4, whereas we do recognize root 3 over 2, it might be that you just have to go to your calculator and get a decimal approximation, and then be smart about how we handle our symmetries out here. And again, I literally can't do this if I'm not drawing the picture. You have to draw your picture and say, okay, I got one of them from my calculator. Where might another one be? Is there something else that has that same height or same width on my unit circle out there? And there's almost always going to be two answers unless you're at exactly our extremes on the unit circle out there. Right? Cool. So this was sort of the same as the last example. It just had some crappy numbers to deal with. That's the only real difference right here. Right? So let's go ahead and do one now where there's a little bit more excitement right here. So two things that you should notice right away about this problem. One, we're being asked to find the solutions just in this interval right here. So in this problem, I have, there's not going to be any k business. We're just going to find the particular solutions associated with the interval from 0 to 2 pi. The other thing that you should notice about this problem that's going to make this much more exciting is that there is a 3 theta on the inside right there. That means that we've got to be doing a little bit of more math after we've done our inverse sine function here. So let's go ahead and do this, guys. So starting with 2 sine 3 theta equals -1. My goal is to solve for theta, right? So I'm thinking to myself, well, sine of 3 theta is going to be -1. And here's a really useful thing that I think that you should do for yourself. This is a bit overkill, and I don't expect everybody to write this every time, but I'm going to write it this way right now because I think it's a good thing to like see once, just to make sure that there's not confusion about when certain steps occur. What I think is a useful thing to do right now is to stop and think about this as sine of x equals -1. Don't let that 3 start jamming up your thoughts right now. What I need to ask myself is, when does this happen? When do we take the sine of an angle x? Don't worry about the 3 right now. When do we take the sine of an angle x and get -1? Well, on my unit circle, I actually know there's only one solution. Right? It's that guy sitting right down there. We have a height of -1. I'll keep drawing my little dashed lines right there. There's my y equals -1. Only one solution. And very importantly, I'm finding it to be x equals, what are we getting here? -3 pi halves. Now, here's the tricky part to this problem here, is that I am still going to have value in stating my general solutions here. Right? So here's what I want to say. Our general solution for x and we could certainly do more rotations, right? Plus 2 pi k. You could do another lap and land there again. Do another lap and land there again. All those should be good. 3 pi halves. Our next one would be -3 pi halves. Our next one would be, oh wait, sorry. Oh, wait a minute. Sorry. I need to back up 1 second right here. I did two things at once here. This is either +3 pi halves or this is -1 pi half, right? We either go backwards in rotation by pi halves or we go forwards in rotation by 3 pi halves, one or the other. I'm going to ditch that and ditch that right there, all right? So 3 pi halves plus 2 pi k. That's our general solution for this guy. But what I know is right here, the very important thing that I did right here is I said, let's define x to be 3 theta. Our goal was to find theta, not to find x. So now that I've found a general solution where and notice what I did here is I was like, oh, I don't want to deal with that 3. I'm just not going to. I'm just going to ignore the 3 for right now. That's what I did by making my variable of x equals 3 theta, right? But now I've got to come back and deal with that 3, and I need my general solution to help me do that. So what I'm now going to say is 3 theta is equal to 3 pi halves plus 2 pi k. And now I can easily solve for theta by dividing this whole equation by 3. All right? So now we get to cross over the page right here and say, get out of here, example. And say theta equals, I'm going to divide everything by 3. 3 pi halves divided by 3 is just 1 pi half. Plus, it looks like a 2 pi thirds k. All right, 2 pi got divided by 3, and it's very typical to just always leave your k as like a floater, because your k is your representative of your number of revolutions, number of additional components, but it's no longer one revolution. It's 1/3 of one revolution, right? 2 pi over 3. So this is our general solution for theta. So now we can come back what are the particular solutions? In the interval from 0 to 2 pi. Well, let's just go ahead and bust out a list right here. I mean, let's just see where this goes. All right, so what I'm going to do is I'm going to say, let's do it like this. Let's set a k list and a theta list right here. And I'm going to do a little bit of overkill right here, but just to kind of help emphasize the point. One thing I'm thinking to myself is maybe k should be negative here. Maybe we'll pick up some negatives. Maybe k is supposed to be -1 first. Well, if I do -1 right here, and by the way, I want to rewrite this guy as maybe for myself, theta equals, I'm going to get a common denominator is basically what I want to do right here. So like 3 pi sixths plus 4 pi sixths, okay? Right, I multiplied this guy by 3 over 3 and this guy by 2 over 2 so that they have a common denominator. I'm going to have to add a whole bunch of fractions here, which is why I want to do that for myself. If I make k -1, then when k is -1, we're going to get -4 pi sixths and +3 pi sixths, which is going to give me -pi sixths. That is a general solution, but it's not in our interval of interest because it's not between 0 and 2 pi. So I'm going to go ahead and sort of, eliminate this one right here. I'm just going to mark it with the red X right there to say nope. So it doesn't look like going in the negative direction is going to be helpful for us. It's going to give us things that come before our interval of interest. If I pick k equal to 0, well, k equal to 0 is easy. We're just going to get pi halves. That is in our interval of interest. I'm good with that one. What if k is 1? Well, if k is 1, when I add these two fractions, 3 pi sixths plus 1 copy of 4 pi sixths is going to give me 7 pi sixths. 7 pi over 6 is more than 0 and less than 2 pi. 2 pi would be like 12 pi sixths. So I'm still good. I'm still in our interval right here. Now let's see what happens if I go to k equals 2. If k equals 2, this is now 8 pi sixths, because I'm doubling this. 8 pi sixths plus 3 pi sixths is 11 pi sixths. That is still less than 2 pi, but more than 0, right? Because 2 pi would be 12 pi sixths. But I'm noticing if I go so far as to go out to 3, then 3 being my k value gives me 12 pi sixths plus 3 pi sixths, that's 15 pi sixths. That's too big. Oops, I'm putting an X there because I'm anticipating saying no to this one. 15 pi sixths, that's more than 2 pi. And so that one's going to be discluded as well. So it looks like we got these three solutions right here for theta as our particular solutions in the interval from 0 to 2 pi. Come on, Microsoft Word. In general, in math, when you're making lists of stuff, you should use curly braces to indicate it's a collection of items right here. And I think those are my three solutions that we're coming up with right there. So, important lesson. here's the deal with this one. Even though we only wanted to find the particular solutions in the interval from 0 to 2 pi, we didn't have a way to do that if we didn't come up with a general solution first. So even if this problem is saying to you, find the solutions in this interval, you should always be, every time you ever solve a trig equation, you should be coming up with a general solution first, then asking yourself, what values of k are going to result in my angle falling within the desired interval? That's always your last step right there, is asking, what values of k are going to make this work to get me in the interval I actually wanted right there, if we're looking for a particular interval of solutions at all. So recognize that we always, always, always want to come up with our general solutions here, especially when we have constant multiples of our theta inside of our trig function, like we had a 3 right here, right? So often what I do, again, let's talk about our strategy here, is I solved all the way down to just a trig function. Sine of 3 theta equals -1. I then said, I don't like that 3 theta at all. If that was just theta, I'd have no problem here. So I kind of did that. I just made a new variable. I said, let just x be 3 theta. I'll think about the 3 in a minute. I said to myself, I know when sine gets down to -1, that's going to be at 3 pi halves right there, right? Positive 3 pi halves rotation to get there. And so I came with a general solution in terms of x, but x is not a variable that I'm interested in. Theta is the variable that I'm interested in. I would have missed 2 out of the 3 of these solutions if I had just immediately gone to dividing the solution by 3. I would have only found pi halves. It was important that we stated the full general solution with the 2 pi k on here before I then divided the whole thing by 3, or else I wasn't going to end up getting these two solutions, right? If we would have just said, oh, this is going to give me 3 pi halves, and divided by 3 is 1 pi half, we're done, we would have missed 2 of the solutions that were out here. So even if you're only interested in finding particular solutions, you have to find a general solution along the way, and then perhaps do your division or your alteration or whatever it's going to look like from this guy right here, to get a general form of all of your solutions for theta. Then ask yourself, what values of k are going to do this for me? And find ones that are too far on the left, find ones that are too far on the right, keep all the ones that worked out in the middle right there. Let's go and double check that I'm not leading you astray here with a little bit of Desmos action. 2 sine of 3 theta equals -1. Let's go check it out. 2 sine of 3 theta equals -1. Y equals 2 sine of 3 theta. And I want this to be equal to -1. So also remember, we were interested in the interval from 0 to 2 pi. So I'm just going to only give myself that. Oh, I scrolled away from it. There we go. And so again here, we're noticing, 2 sine of 3 theta equal to -1. What am I doing? Am I missing some right here? Oh my gosh, I'm seeing what I'm doing right here. All right, so what I'm going to do is I'm going to modify this problem slightly so that the work that I did fits the problem. I did a dumb thing here at the very beginning of this problem. I literally just straight up dropped my 2. Where'd that 2 go right there? I went to go divide by 2 right here, and I just straight up didn't. I just dropped that thing completely. So what I'm going to do is I'm just going to do this. Oop. There we go. And I'm just going to do this. Boom, there. Now all of my work is correct. That was dumb and cheap of me to fix that way. I just forgot to do a division by 2. I want to point out what the difference is right here. If that would have been a -1/2, then there would have been 2 solutions instead of 1 solution down there. So we would have ended up getting, I believe, 6 solutions instead of 3 solutions from the branches of those 2 solutions getting 3 each when we divided by 3. And so when we look over at Desmos for my incorrect version here are the 6 solutions that we would have gotten. I am going to go ahead and just drop this 2 and watch this become only 3 solutions right there. And in fact, you can even see the branching happen right there. Watch this happen. I'm going to have a slider for A, and watch as we go from 1 to 2. That 1 touching down there turns into 2 solutions, right? It's sort of like broke off into those 2 solutions. That's these symmetries that we're seeing when we've done with our previous sine and cosine examples. There's often these 2 solutions within the unit circle unless you are at your extremes right there, whereas here we were touching at the extremes right there. In any event, here we're getting our pi halves, 7 pi 6, 11 pi 6. Those are the 3 that I came up with for my slightly wrong problem right there. Sorry, I forgot to divide by 2, but my math worked out if I had just forgotten that the 2 was there. Or if I throw out the 2, I know that you guys don't get the opportunity to just change your my open math problems right here, but the math that I did was correct just for the wrong problem right there. The big idea of this problem remains, which is you have to keep a general solution for these things before you go finding particular solutions, especially when we have this constant multiple of theta inside of our trig function right there. That's really important for this guy. All right, so, oops, did I write the wrong thing anywhere else right here? No, I think I'm good with this now. All right, a little embarrassing. That's all right. We still got through it. Let's do 2 more examples here. This example right here is going to be good because it's going to, oh my gosh, it's going to involve a little bit of an identity here. I'm going to start thinking about those. And our last example that we'll do for the day will involve a word problem, something I'll expect you guys to do on our upcoming homework assignment here. So let's get back to this guy here. So find the general solution to the equation sine of theta plus cosine of theta squared equals 0. Okay. So this one looks a little bit tougher right here. It's not really clear what we're going to do. A big thing that makes this one hard right here is that we have both sines of theta and cosines of theta. In all of our previous examples, there's been one trig function, sine of 3 theta, sine of theta, cosine of theta, sine of theta, right? There's just been one trig function in all the examples we've done so far. This one's got 2, and that's a bit of a toughie for me right here. So it's not clear what you have Word, Microsoft Word. Do we need to have words right now? Do we need to talk about this? Why are you behaving different to me in the afternoons than you always do otherwise? I don't appreciate this very much right here. Oh, you're doing it to me again, buddy. Okay. You need to stop bringing that thing up and you need to, oh my gosh, oh my gosh, oh my gosh. The computer is on the weekend. So, again, the thing that sort of scares me about this one is the 2 different trig functions being in here. It's not clear what I want to be doing here. I'm going to caution you against the idea of taking a square root on both sides right now. We're going to talk a little bit about that more in 7-8. I know that's a couple weeks away. But what I'm thinking to myself right now is, well, I know what it's like to square something. I know that squaring something is like multiplying it by itself, right? So maybe I want to think about this as sine of theta times, or plus cosine of theta times sine of theta plus cosine of theta. That is sine of theta plus cosine of theta squared, right? And so if I were to multiply this guy out, I'm going to FOIL this out. My first times first is sine squared. My outer is sine times cosine. My inner is also sine times cosine. And my last is cosine times cosine. That's a cosine squared. Now, do you recognize any stuff in here? Well, one thing I am immediately seeing is the one that everybody should be catching, always. We're adding sine squared plus cosine squared. That's just equal to 1. I know that one. The other thing I can see is that these 2 terms in the middle are clearly the same as each other. So it looks like I'm getting 2 sine theta cosine theta plus 1 equals 0. Right? So I don't know, did that help me? Well, kind of. And here's the thing I'm thinking. I yelled at you guys about this a little bit in our last video. It's often difficult to solve equations where you're adding 2 quantities together. It's often more simple to solve an equation where you have a product of 2 things being multiplied together. This is often helpful because we get something called the zero product property, which, by the way, we're going to be either, we can take advantage of that sort of, well, we can't really because we don't have a product equal to 0. We have a product plus 1 is equal to 0. This plus 1 is kind of jamming us up right now, so maybe I'm thinking to myself, let's at least add it over to the other side and then stop and consider our situation for a second right here. I can't use the zero product property. There is no such thing as the 1 product property, right? When you multiply 2 things together, you get 1. It could have been anything. 7 and 1/7, 14 and 1/14. It's not like I know one of them for sure. If we multiply 2 numbers and get 0, one of them 0. I can say that. Can't make that statement about any number that we're equal to other than 0. So one thing that we might want to do right now, I get like divide by 2, but what's that really going to help us do? I still have sine times cosine This is awkward because I'm looking to make a statement that says theta equals, but I have theta in two different places and I don't quite know how to get them together. Well, as soon as you get stuck in situations like this, you should say to yourself, do I have some nice way to rewrite sine times cosine? I don't know. Let's go see. Do we have some nice way to rewrite sine? So now I'm just doing a blind search out here. Where do I see sine times cosine show up? Well, here's one. Here's sine times cosine. This would involve more cosines times sines and sines of sums right here. That seems like it's not going to be helpful, even though it's technically what I'm looking for in a sense. And that kind of goes for the rest of these. Like I'm hoping this is not what I have to do right there. Nothing really else down there. No sine times cosine here. Ooh. Now this seems nice. That guy right there seems kind of nice for me. Two reasons why. One, there's even a 2 sitting out front like we have. Also, it looks like this is a way to rewrite this in terms of a single trig function. That's extra nice. It's taking us from our side of the equation having two thetas, two separated thetas in it, to having a single instance of theta doubled, but we can deal with that by now from the last problem. This looks like a really useful identity for me in this scenario right here. So it looks like I'm able to say 2 sine theta cosine theta is just straight up 2 or sine of 2 theta right there. So let's go ahead and make that swap over here. And it looks like we're back in an incredibly similar position to where we were with my modified version of the previous problem right here. I know that sine of 2 theta equals 1. I can find this guy right here, right? So I'm gonna again do my like swap out for x right here. So I find my general solution first. I'm gonna think to myself, sine of theta, sorry, sine of x, because I'm going to create my new variable here. And again, this is not really a necessary step. I just do this to like force myself to think the right things. On my unit circle right here, the only place this is going to give us solutions, this gives x equals, so sine as a height getting to positive 1. I know that's going to occur at pi halves. And then it's going to also occur every 2 pi beyond that, right? So that's my general solution for x. But I now know that 2 theta is going to be equal to x, right? I'm going to divide everything by 2. And I'm going to be getting here pi fourths plus pi k. Were we looking for a general or a particular here? General solution. So it seems like that's my general solution. So I want to kind of show you why I could have anticipated this being my correct general solution. Here's why I kind of knew to expect to see pi fourths crop up here. In our original problem, what we were really looking for was basically adding together sine and cosine to get 0, right? And kind of what I'm thinking to myself is these two basically needed to add together to make 0 independent of that squaring, right? Because 0 squared is 0. It's the only way to get to 0. I'm saying I squared a number and got 0. What did I square? Well, 0, obviously, right? So it seems like sine and cosine need to be the same number, but opposite of one another. And what angle results in sine and cosine achieving the exact same values? Well, there's only one family of angles, and it's our pi fourths, right? 1 pi fourth, 3 pi fourths, 5 pi fourths, 7 pi fourths. But what I'm also noticing right here is that, oh dang it, I did some stupid math over here again. I'm getting the wrong number right here. Oh my gosh, I don't know why I'm doing these tiny dumb things here today. Oh, this is frustrating. I'm gonna fix this one instead of just change the problem again. That's a -1. I subtracted 1 over. What am I doing right here? It's a -1 right there. I'm gonna go down here. It's a -1. That's a -1. My picture is wrong. That dot goes at the bottom now. Oh my gosh. Oh my gosh. And this is why it's always good to check your answers, because otherwise you're going to do stupid things like me and make a bunch of mistakes. This is going to give x equals 3 pi halves plus 2 pi k. I'm dividing that by 2, And I'm now getting what? 3 pi fourths? Now I'm getting the answer I expected to get. It's still in the fourths family, the pi fourths family, but it's some other ones. All right, now I'm dividing by 2, and I'm getting what? 3 pi. Oh, now I'm double confusing myself. I just tried to do my division, and I wasn't at my division step right there. So I'm going to write this as the 3 pi halves. And now I just got to slow down because now I've flustered myself here. Man, apologies. I wish that I wasn't making these kinds of mistakes here. Now I'm going to get that out of here. Now let's just write it. 3 pi currently divided by 2. I'm dividing by an additional 2, so it's like dividing by 4. And now I'm going to write a 2 because I'm thinking that, and I still can't write correctly. This should be 3 pi over 4. 3 pi over 4. So when I think 3 pi fourths, 3 pi fourths to me is this guy. So how did I know that my previous one was wrong when I got that pi fourths right there? Here's how I knew. What I know up here is I'm thinking to myself, the only angles that give sine and cosine values to be equal to each other is the pi fourths family. But if we're in the first quadrant looking at positive pi fourths, here sine and cosine are both positive. They're not canceling each other out, they're doubling up. However, over here in the second quadrant, my cosine's negative, but my sine is positive. So I'm going to get a negative root 2 over 2 from the cosine, a positive root 2 over 2 from the sine, and they're going to go to 0 together. In the third quadrant, they're both negative, so they're doubling up to give me negative 2 copies of them. But in the fourth quadrant, again, opposite of the second quadrant, we're going to get a positive value for the cosine, so a positive root 2 over 2, a negative value for the sine, a negative root 2 over 2, and they're going to cancel. That's kind of how I knew that was going to happen. Whenever I'm adding together sine and cosine and getting 0, the only things that are going to do that is my pi fourths family, getting some terms appropriate from the pi fourths family there. So here I'm seeing my 3 pi fourths plus pi k. Now that I introduced my negative and actually got that correct right there, let's go ask Desmos if I did this correctly right here. We're looking for the solutions to sine of theta plus cosine of theta squared equals 0. So I'm going to go over here and do, let's get our sine of x, and I want to get some parentheses first here. Sine of x plus cosine of x squared. Oh, come on, Desmos. Help me wrap it up here, man. There's that guy squared. I don't need this. And I want to know when is this equal to 0. And I'm going to see here. There's my 3 pi fourths. There's my 7 pi fourths. These are the 3 pi fourths family. This is 3 pi fourths plus 1 pi got me to my next one. Plus 2 pi would get me to my next one. Plus 3 pi gets me to my next one. These are exactly the solutions that we ended up with right here. The 3 pi fourths plus only pi k because we divided everything by 2 with that theta right there. All right, I'm going to go ahead and not make any mistakes on our final example right here. I swear I'm going to get this whole thing square. All right, final example. This one's different because this one is about a more complicated equation right here. This is exactly based on an example that I just pulled this out of our section 6.8 notes right here. All right, so back in section 6.8, we did an example where, given a table about monthly average temperatures in Denver, we determined a sinusoidal equation that predicts the temperature given the month of the year. We did this together as an example in the video. This is what we came up with. You can go back and look at your 6.8 notes and 6.8 video. This is the exact equation that we came up with looking at just these values in the table. In this case right here, y is our output. It's our predicted temperature. X is our month of the year. And remember, this x minus 1 was occurring because rather than starting at x equals 0, we typically sort of think our counting starts at 1 for January instead of like 0. 0 months have passed if you're in month 1. 1 month has already passed if you're in month 2. There's always that little off by 1. That off by 1 is handled by that x minus 1 right there. So my question for you is, suppose you didn't have access to the table right here, but you did have access to this equation. Right? The question is, at what time can I expect the temperature? And when I say time, I mean like in what month can I expect the temperature to be 50 degrees, right? So we use the table to build the equation, and now we're trying to use the equation to make predictions that we can kind of see in the table, right? So like in this case, like the answer would be like if you have the table, like probably just look in the table. So I'm saying, suppose you don't have access to the table, but you're given this equation, right? Which is typically the way that you're going to see these problems anyway here. When should we expect to get 50 degrees, right? And the thing that I'm kind of seeing here is like, it seems like we should be getting a number that's like, I don't know, between 9, like around 9 or 10 right here. And it seems like we should be getting another one around like 4 and 5 right here, right? Those are the things that I would expect to see for x values given the y value of the temperatures here. So let's see if we can go ahead and actually do the math to solve this equation for the desired x value. And notice, the really important thing here is we're not plugging in x's and getting out y's. That's the sort of forwards direction. That's the evaluate direction. We're plugging in y's and solving for x. It's the undoing direction, the solving versus evaluating direction right here. So we want to start with this equation, but we know that our desired output for y is 50, and we want to solve for x. Let's see if we can do this here. Now, how many mistakes am I going to make? That's the question. So 50 equals negative 21.9 cosine of pi sixths times x minus 1 plus 51.6. So we've got all the parts in here. Constant multiple on the outside, additive on the outside. Constant multiple on the inside, additive on the inside, right? We have all 4 components of our general sinusoidal function here. We got to get rid of all of them effectively over the course of this here. So let's go ahead and try and do this here. So what I'm seeing here is the first thing we should always undo is our addition subtraction. So I'm going to subtract 51.6 from both sides. Subtracting 51.6 from 50 should be giving me negative 1.6 over here. Next up, we want to undo our multiplication and division. So I'm going to go ahead and divide by the negative 21.9. So negative 1.6 over negative 21.9. That's going to leave me with cosine of pi sixths times x minus 1. Right? So we've reduced ourselves down to just a trig equation, right? Cosine of pi sixths times x minus 1. And I'm going to do the same trick that I've been doing here, right? This is equal to, let me go to my calculator real quick here, 1.6 divided by 21.9. I'm getting 0.07306. I'm going to round a little bit here, but not too much, because I know that trig functions deal with small numbers. Like, I don't want to just round away. If you just round this to 0.07, I think we'll be off by a little bit here. So I'm going to keep a few more decimal places here. So 0.07306 is what I'm seeing for that guy right there. So what I'm going to do for myself now is I'm going to go ahead and do that thing that I've been doing, where I'm going to say to myself, let's just make a new variable, because this is scary on the inside. I don't want to have to be thinking about that right now. What I want to be thinking about to myself is that I know that on the unit circle, if I took the cosine of some angle and got out this positive number, then that means that there should be some x value on the unit circle that's going to give me that guy, right? So I'm expecting there to be this solution and this solution. And when we looked up here in the table a moment ago, we said, yeah, it looks like there's about 2 times a year where we expect the monthly temperature to be about 50, around month 4 and 5, as well as around month 10 and 11 right there. Those are the things that we were expecting right there, right? So what do we really, get out of here. So what I think so that kind of agrees with this right here. So this is my x equals 0.07306. So what I want to do is this. I'm going to make a new variable, and I'm going to say, let's let y be our pi sixth times x minus 1, right? That's going to be my little variable swap. So I can, and again, every time I'm doing this, what I'm doing is I'm saying, I don't want to think about that part yet. I don't want to think about the pi sixth and the minus 1. I just want to undo this cosine part. This is me like trying to handle each component piece by piece, rather than trying to be like, and the answer is, well, like it's too much to do all at once. So I'm kind of, this is me saving some work for later is what that's doing. So I'm going to say here cosine of y is 0.07306. I'm going to go to my calculator and get a value for this guy. I'm going to get my cosine inverse of 0.07306. Now what I know is that since cosine measures left to right amount, our cosine inverse function always only gives us the outputs on the top half of the unit circle. So my calculator is going to tell me what this angle is up here. I'm going to have to figure out what this angle is down here. Fortunately, our symmetry on this one's a lot easier. This is going to be a positive theta. This is just going to be a negative of that same amount of theta right there, right? So the symmetry idea is going to be much, much simpler. So going to my calculator and hitting this guy up right here, I'm going to do a cosine inverse, and I can actually just keep the whole answer because I have that whole decimal sitting in my calculator right now unrounded. When I do cosine inverse here, I am getting 1.4977. And this is this guy right up here. If this is theta, picking a color here so I'm not overlapping all my colors. If this is theta, then this down here is just negative theta to get to my other point that's over there. So I'm going to be able to say by symmetry, we also get y equals negative 1.4977 radians. Those are my two values that are going to land me at a cosine output of 0.07306. So what I don't want is a y solution. What I want is an x solution right there. Oh, y was a bad variable name considering we already had that used up top. See, I knew I was going to make a mistake I didn't want to make right there. That's okay. This one's just a naming mistake right there. I'm just going to name this thing theta instead since we haven't used a theta yet in this problem. So theta equals theta equals theta equals. So what I now want to do is now convert theta back into x. So when we made this variable substitution in green, what that was saying to me is, don't think about the pi 6 and the -1 for right now. Save that till later. Let's deal with the trig functions first. We just dealt with the trig function by, in a sense, just imagining a simpler problem for ourselves, just cosine of theta equals a number and solving it. Now we can say, okay, it wasn't really only cosine of theta. It was actually cosine of all this mess on the inside. Now let's take care of the mess. All right, so here's what I've got for myself. This is my relationship right here. So what I'm going to say is theta equals pi 6 times x minus 1. And I'm going to branch this into the two different thetas that we've got. We have two different thetas that we've got right here. I want to solve them both for x, right? So 1.4977, that's my theta, equals pi 6 times x minus 1. Also, negative 1.4977 equals pi 6 times x minus 1. Over here, I'm going to multiply by 6 and divide by pi. And I'm going to go ahead and add 1 to that quantity right here. And so let me go to my calculator and do this. I got 1.4977 times 6 divided by pi. That's going to give me 2.86, very close to 2.86 basically. Over here, we're going to get like the exact same math, right? This is going to be like 6 times negative 1.4977 over pi equals x minus 1. So I'm going to get a negative 2.86 equals x minus 1. I'm going to add 1 to both sides, and this is going to give me a negative 1.86. Now, how do I interpret the month negative 1.866? Well, this looks like this is going to be late March right here. What's going on over here? Well, this is like saying this is like about 2 months before the year started. So since months repeat every 12, let's go ahead and add 12 to this guy. And if we do that, I should be getting 10.14 equals x, which is, looks like early October. And this agrees with our table up here. Let me go. So we found 3.86 and 10.14 are effective months that we're interested in right here. And 3.86, it looks like this is, so I think that we're doing this like off by one business right here. You should notice that this is like one below and this is like one below. And I think that that's the reason we're getting our between 10 and 11 right here and between 4 and 5 right here. And wait a minute, we got the 10.14. 10.14 is exactly what I was expecting right there. What, are we off by like a little 1 right here with our other one? Or is this just where our curve got a little bit lumpy out here? So the thing that we want to remember about this is that this equation is something that we came up with. This is not a perfect sine curve right here. So maybe this is where there's a little bit of that distinction between our data points and the actual function itself right here. But again, our process here of solving this was giving us our predictions. Our predictions aren't necessarily going to rematch the data since our curve did not perfectly fit through the data that we were looking at right there. But this is saying if this is our curve that's predicting for us our temperatures based on what month it is, then this prediction would tell us to expect this to happen in late March where we hit 50s. Apparently our data suggested that we're actually going to hit our 50s a little bit closer to being within month 4. So maybe something like 4.15 would have gotten us there or something like that. We estimated a little bit earlier based on our curve. I think that's just giving us our discrepancy between, or if you remember this one, like we plotted 12 data points, but our curve did not exactly fit through those. So there's always a little bit of discrepancy between the data points and the estimating curve. Here we're using the estimating curve to make a prediction. Our predictions are not necessarily going to match exactly with what's ending up being seen in the real world, but I think that you guys are all down with the idea that in places that actually experience winter, unlike here, it's pretty typical to experience the beginning of true cold weather in early October, and then you exit it in late March where it's starting to get warm again out there. So our process is still good here. I'm still doing algebra. So at the top here, this is only algebra that happened right here to solve for the trig function. Once I got down to the trig function, I said that inside of that trig function is gross. Let's just call it something as simple as possible, just an angle, just to pick a variable I haven't used yet, which is my stupid mistake of calling that y when there was already a y technically involved in the problem right here. So I called it some other variable so that I could just think about undoing the trig part of this problem. Once I dealt with the trig part, gone to my calculator to get one angle, identified my symmetry to get my other associated angle, I then said, okay, those are my angles in theta associated with cosine, but I really wanted actually x. So I want to now undo the substitution that I did. This substitution made it easy for us to do our trig thoughts right here, but it made it one step away from our actual final solution. So then I said, let's get back into X land by undoing that substitution and do the algebra to solve. And while this technically doesn't agree with our data, this point right here does agree with our curve. And so maybe it's my final thing to do here for the day. Let's go ask Desmos if it agrees with what we're doing right here. I think Desmos is cool with me copying and pasting here. Let's find out. Kinda. It just didn't like my bracket right there. That's weird. Oh, it just gave me bonus brackets right there for no reason. So let's just get this rewritten in a way that I think Desmos will actually think about it. Pi over 6. Ah, it did it to me. Okay, that's okay. Cosine of pi 6 times x minus 1. Plus 51.6. We wanted to know when is this equal to y equals 50. I know I got to go up because I'm looking for y equals 50. And I am seeing here that within the first year, we're getting 3.86 and 10.14. Those are exactly what we came up with by hand right there by solving that using our unit circle for those things out there. And notice, by the way, here is our negative 1.86 that we came up with, but we decided to add 12 to that since months are cyclic with period 12 to get to the 10.14 solution that was out there. So this graph has all three of the kind of solutions that we saw out there, but negative is a weird way to reference months. So we referenced our solution with these positive ones right here. Cool. So we can do the by hand math to solve these guys now, which is the really important thing. So remember, Desmos is definitely a great resource for you guys to always be checking your answers out here. Also remember that when I go to ask you for things like this, especially on your midterm, the only thing I care about is seeing your math right here. And I have zero interest in seeing calculator produced answers right here. So being able to actually do the algebra, do the trigonometry, dealing with substitutions, interpreting things in the context of a problem, x equals negative 1.86 is not anything I'm ever worried about unless the context of my problem is what month is it. If you were to tell me, oh, it's the negative 1.86th month, then I have a problem with that, and we want to fix that so it fits the context of our problem. That's right there, right? So that's going to wrap it up here for me today for 7.7. This is our last video now for a few weeks. Next week is spring break. Week after that, you're only going to be taking a midterm. It's not till the week after that we're going to come back and we're going to do 7, 8. So the very next video, although it's not going to be for 20 days from right now, is going to be more on solving trig equations. So you should expect to see a lot of stuff like this, but you should expect to maybe see a little bit more stuff that looks like this problem did right here, where we need to do a little bit more heavy algebra and where we need to use our identities to help replace quantities we can't handle with solving equations with ones we can handle with solving equations. And hopefully you guys don't drop 19 negatives and forget to divide by 2 and call your variables names that have already been used before like I did in this video right here. Watch out for your small mistakes. And again, while I'm uninterested in seeing Desmos solutions to these problems, use it to verify your work. It's how you catch your small mistakes. I made so many stupid mistakes today that weren't based on, I knew what I was doing, I just wrote stuff wrong. A lot of technology to help you catch those errors right there. It's a very useful tool. We still want to have understanding of a concept rather than just an ability to use a tool. These are two different things, and I will certainly be interested in seeing your ability to understand a concept when I ask you to solve these types of equations here. So have a good one. Have a good spring break. Good luck on the midterm. I'll see you guys in section 7.8 in the last week of March. Have a good one, everybody.